In this video, we'll look at two concepts, AC signals and impedance. Often the signal of interest varies rapidly with time. A sine wave is a good example of a signal that varies in a periodic fashion with time. We say that the signal has an alternating component, and that's what's meant by an AC signal. It doesn't necessarily mean alternating current. Recall that the sine function can be thought of as the y component of a clock hand as it moves with time. Admittedly, it's a strange clock since it starts at essentially 3 o'clock and moves counterclockwise from its starting position. But like a normal clock, it moves at a constant angular velocity. This angular velocity has units of radians per second. The angle that this hand sweeps out with respect to the origin is just the product of the angular velocity and time. The value of the sine wave changes with time. Its instantaneous value is equal to the y-coordinate of the vector as it moves around the unit circle. If this happens to be a current signal, then the instantaneous current is the y component of the vector as it moves around the unit circle. The period of the wave is the time that it takes the hand to move one revolution around the clock. It is also the distance on the time axis that the wave moves before it repeats itself. We typically report the period in seconds. The frequency for a periodic signal is just the reciprocal of the period. Therefore, it has units of reciprocal seconds or hertz. The frequency and the angular velocity are related. Omega equals 2 pi f, so the angle at any given time is 2 pi ft. We often measure the peak height from the center, or the average vertical position, and we call that the amplitude or magnitude of the wave. Here I'm using a capital I for the peak or maximum current. The instantaneous current, or instantaneous signal, is equal to the maximum current or maximum signal times the sine of the angle omega t. Or in terms of the frequency, this is equal to I max times sine 2 pi ft. An AC signal can have a phase as well. What do we mean by that? Imagine this yellow curve is a reference signal. The red curve has the same frequency and amplitude, but has been shifted along the time axis. We say that it has a different phase. One way of expressing the phase difference is in terms of a phase angle. That's the angle that separates the signal rotating vector around the unit circle from the reference vector rotating at the same frequency. The amount that the wave has been shifted with respect to some reference signal is known as the phase shift, or delta t, when expressed as a displacement in time. Phase shifts and phase angles provide important information in experiments like NMR. Of course, the phase angle and the phase shift are interrelated. The phase angle is equal to 2 pi times the delta t, or phase shift, divided by the period t for the wave. In the lesson about capacitors, we noted that these devices limit current in a time-dependent manner. Up until now, our best description of the relationship between current and voltage has been Ohm's law, or V equals IR. How do we model the effect of capacitors on current and voltage as well? Mainly, we need to generalize Ohm's law in terms of impedance in place of resistance. A complete description is beyond the scope of this course, but we'll discuss impedance in an operational manner in order to apply it to some common situations. In order to model the time-dependent aspects of electronic devices, impedance is defined as a complex variable and one that is a function of frequency. Here we're using j to represent the square root of -1 instead of I to keep from confusing it with current. So the impedance has a real part and an imaginary part. The impedance for resistors is all time independent, so Z equals R, or the resistance for a resistor. X equals 0 for a resistor. The impedance for a capacitor is all in the imaginary part. It's minus J over omega C, or minus J over 2 pi f C. Occasionally, we use devices called inductors. These are coils of wire where the magnetic field associated with the current interacts with the current in interesting ways. The impedance for a pure inductor has only an imaginary part. It's equal to omega Lj, where L stands for the inductance of the coil. For a simple circuit with a resistor and capacitor in series, the net combined impedance is just the sum of the impedance of the individual components, or R plus a negative J over 2 pi fc. The quantity that's measurable in the lab is the magnitude of the impedance. The magnitude of the impedance is the ratio of the maximum or peak voltage divided by the maximum or peak current. We can predict that value from the square root of the sum of the R term squared plus the X term squared. And expanding that, this is what we get for the simple RC circuit. Recall that we can measure the voltage across the capacitor to filter out or remove high-frequency components and pass only the low-frequency components. The output voltage at the capacitor is then the fraction of the signal voltage, and the proportionality constant is the ratio of the magnitude of the impedance for the capacitor to that for the resistor and capacitor combination. And expanding that, we get this expression. A plot of the output voltage versus frequency looks like this. At low frequencies, the output voltage is the same as the input voltage V sub S, but then it rolls off and goes up to 0 at high frequencies. It is interesting to note that it rolls off around a frequency equal to 1 over 2 pi RC. At that frequency, V out is equal to Vs over the square root of 2, or 0.707 times V sub S. That would appear right about here on the curve. We can also predict the phase angle between the voltage across the capacitor and V sub S. It is equal to the arctangent of the X component over the R value. And in this case, that gives the arctangent of 1 over 2 pi FRC.